All right, let's go ahead and get started. Before we do, anybody have any questions about anything? All right, so we're continuing section 2.4, product rule, quotient rule. So now instead of looking at a specific function, I mean, these are specific functions, but we don't have the definitions we usually do. So I want to find the derivative of these two functions, capital F and capital G, at the x value of -1. So how can I start doing that? What should I probably look for first? If I want to take a derivative of capital F, how would I have to do that? I have to use the product rule, right? So then based on the two smaller or the two simpler functions that's the product of, what would that derivative be? Essentially, how does the product rule work? Yep. So I should stop right there. Hopefully that looks familiar. Maybe you don't have it totally committed to memory yet, but this is what we're going to have to do. So if I want to find the derivative of this function capital F, this is how I have to deal with it in this constituent parts. So there's the derivative. Now, how do I evaluate this thing at the x value that I care about? Are we okay with what I'm doing here? All right. So what are these values then? What is f prime of -1?
12.
So 12 multiplied by -3 plus what? Good. So multiplying this together, I get -36 plus 40, which is equal to 4. Any questions about how we got there? Was a lot more quiet than I'm used to. All right, so if that's f prime of -1, capital F prime of -1, what's capital G prime of -1? How should I start attacking that? What's the
quotient?
Yeah, so we need the quotient rule. How come?
Because it's division.
Right, so I'm dividing lowercase f by lowercase g here. So what is this derivative? What is the quotient rule?
Prime of x times g of x
F prime of x times g of x
minus f of x times t prime of x
minus f of x g prime of x.
all over bracket g of x squared.
Yep. Running out of room, but no, what do I have to do to this to evaluate for the point where I want it?
Plug in -1.
Okay, so I'm going to try to use this margin. So if I want g prime of -1, what's that equal to?
8.
And it should be -36 plus 40, or sorry, minus 40. All over what?
9.
I don't think it's, oh yeah, it is 9, sorry. So that comes out to -76 over 9, which I don't think reduces. Any questions there? All right.
The bottom of the motion was gx squared, right?
Gx squared, yeah.
Okay.
All right, this thing right here, the derivative of tangent of x. Why am I bringing this up when we're talking about quotient rule?
Is it cosine over sine?
Close. Sine over cosine, right? So that's something we can do instead. So right now we don't know what the derivative of tangent x is, but we can decompose it like this: the derivative of sine of x over cosine of x. What is that derivative?
Negative cosine sine.
No. So you cannot just take the derivative of the numerator.
Oh, yes, actually.
Yeah, so
Quotient.
yeah, I've got to use that. So let's go through that. So we know the first term is going to be something involving sine of x, cosine of x, right? Which one of those am I taking the derivative of? Minus sine of x times the derivative of cosine x all over,
Sine x squared.
yeah, cosine squared of x. All right, pretty nasty. Can we simplify this at all?
If it's cosine squared, I think you cancel out both cosine.
Yeah, I'm going to avoid doing that for now, and I'll explain why. Hopefully, question.
Isn't it simplifying to cosine squared x minus negative sine squared?
Yeah, it's just so yeah, cosine squared x plus sine squared x, right? I mean, that's basically what you said. So yeah, derivative of sine of x is cosine of x, so this becomes cosine squared of x. Sine of x times negative sine of x. Subtracting that gives me positive sine squared of x all over cosine squared of x. Does that simplify any further?
Cancel out cosine squared of x.
There's something even more powerful I can do.
Doesn't it just become sine of x?
Cosine squared of x plus sine squared of x equals
1.
1. Sound familiar?
Yep.
Basically, the reason for that is this: if I use the unit circle, something we've said in here before is that this is really bad, but I'm going to keep on going with it. If you have an angle that projects, basically this angle is going to project an XY point here, right? That X coordinate is going to come from cosine theta. That Y coordinate is going to come from sine theta. If I take the Pythagorean theorem there, I get cosine squared of theta plus sine squared of theta will equal however long the hypotenuse is squared, right? How long is the hypotenuse? It's 1, right? I call this the unit circle, so by definition it has a radius of 1. All right, one more thing we can do. 1 over cosine squared of x. Go ahead.
Secant squared.
That's secant squared of x. So think back to your reciprocal trig identities. That is indeed the derivative of tangent of x. Any questions there? All right, so before today, we had derivative rules for sine and cosine. Now, I'm going to give you the rest of them. So we just did, we had these two previously. We just did this one. I recommend, just to get some practice with the quotient rule, making sure you can derive those. But what is cosecant? Cosecant of x by definition? 1/sine of x. So you can use the quotient rule on that to get that derivative back. And same the other two. As long as you get the definitions straight.
So these are like derivatives we should remember, right?
What's that?
These are like derivatives we should remember.
You should, but I'm not going to. So I don't. Sometimes I forget them, but it doesn't matter because I know how to. I can reconstruct them out of simpler stuff. So, yeah, memorizing is good. It's always better to kind of be able to build them up if you need to. Anything else? All right. How about this thing? I want to find dhdx given that definition of h of x. What do I have to do here? Do I need the product rule?
And
So we need the product rule, right? Why? So if we're saying we need the product rule, then we are. Garrett, you got something?
Isn't it because x is multiplying 2 tan x plus 3?
Yeah, so basically what's inside the square brackets multiplied by what's outside the square brackets. So I have h equals f times g. F of x is going to be equal to, let's say, 7x squared, and g of x will be equal to 2 tangent x plus 3 secant x. I think we can do f prime of x. What is it?
14x.
14x. Can I do g prime?
Yeah. To
Hopefully 2 tangent x is somewhat fresh in your minds. Garrett?
and 2 secant x squared.
That'll be 2 secant squared x. And 3 secant x, we didn't derive that formula for the derivative of secant x, but I kind of gave it to you. What's the derivative of secant of x? Did you write it down just now? How we doing? All right, so I have all the pieces. Now can I get the full expression for this derivative? What is dh dx?
X times 3 secant x tangent x. Oh, wait. 2 secant squared x plus 3 secant x tangent.
We don't multiply the two derivatives by one another.
14x
So-
times 2 tan x plus 3 secant.
There you go. So there's the first term plus what?
7x squared. 2 secant squared x, 3 secant x.
All right. Yeah, we kind of could have got the quotient rule involved here, but we don't really need to. So I think this is complete. Any questions there? All right. How about this thing? Do I need the quotient rule?
Yes.
Yep. Do I need the product rule?
Yeah.
Gotta use them both, right? So let's think about how to break this thing down. So we've agreed that we have to use both rules. I have a product and a quotient I have to deal with. So how many functions should I break this thing into?
Two on top of one bottom,
Okay, so and the one on top, you want to have that be,
x cubed and sine of x.
okay.
Sine of x.
So we'll do this. We'll call them a of x times b of x times or divided by c of x. Might as well define all those things. A of x is equal to x cubed. B of x is equal to sine of x. And c of x is equal to x plus 1. All right, so those are my 3 building blocks. What should I do with them? Go ahead, Garrett.
Multiply a of x by b of x.
Multiply them?
The,
Oh, you're on, okay, so take the derivative of that. Okay, so yeah, let's take the derivative of that. Does it make sense to find the derivative of all these individual pieces first? I mean, if we're going to do the numerator, we at least need a prime and b prime. So what is a prime and what is b prime?
3x to the second.
3x squared
Cosine x.
cosine x. All right, so from there, what's the derivative of the numerator going to be?
Three x times sine of x
So 3x squared sine of x
plus x cubed cosine x.
Okay. This right here is equal to this product, ax, bx. That derivative. All right, so I think that's a really good step. How do I keep going?
With ax dx prime over x plus 1 in the quotient rule.
Right, so now I gotta use the quotient rule, right? So, and we got to be careful about how we do that. So what's the first term in that quotient rule going to be?
That whole thing.
Which whole thing?
Ax dx prime.
Okay, so, and why is it that? Let's talk about that while I'm writing it.
Because it's in the numerator.
Okay, so yeah, because my first, the first product I'm going to have in my numerator for the quotient rule is going to come from the derivative of the numerator. And this is multiplied by what? Okay, x plus 1. So derivative of the numerator times the denominator minus what? Okay.
x cubed sine x.
X cubed sine x times just d1, right? Where's that 1 come from?
Derivative of cx.
The derivative of the c function. All of that divided by
Square root.
not 1 squared,
X plus 1 squared.
x plus 1 squared. Very good. How are we doing there? All right. All right, sine squared of theta. We'll find the derivative of sine squared of theta. So how can I start working towards that?
product rule here?
If you would use the product rule, how would you set it up?
It would be sine squared of that.
Yeah, but do we know how to take, do you know what the derivative of sine squared is?
Is it not cosine squared?
No, it's not. So if we're gonna set this up as a product, we gotta break it down into things we know how to work with right now. So I agree that setting up as a product of two things is good, but we need to be careful about what those are. What are some things I can multiply together to give me sine squared, but I also know the derivative about those individual functions? Okay.
Isn't it sine times sine?
Yeah, the sine of theta times sine of theta. Do we know what the derivative of sine of theta is? Not sine squared, just sine of theta. Right, so we can do that. So if I call both of these individual pieces sine of theta, I can use product rule with this thing. So from that setup, what's the derivative of sine squared of theta?
Cosine theta times sine theta
Cosine theta times sine theta
plus sine theta times cosine theta.
plus sine of theta cosine theta. We can simplify a little bit, right? Any questions there?
Is it not two cosine theta or is it
2 cosine theta?
yeah, like it's two sine theta?
It's two sine.
All things are, all those are multiplied by each other. 2 times sine theta times cosine theta. Any questions about that? All right, let's go one level deeper. Let's find the derivative of sine cubed. So, can I set this up using product rule or quotient rule? Good.
Yeah.
As product or quotient?
Oh, product.
Okay.
2 sine. Yeah, it's 2 sine.
So the first thing I do is this. If you're telling me we can use product rule, then that means we are saying that the function f, I can break that down into g of theta and h of theta, where when I multiply those together, I get sine cubed. So there are things I know the derivatives of that I can multiply together in that way. Here, try again.
And then sine squared. Sine squared times sine.
Do we know the derivative of sine squared theta? Yeah, we just did it. So now we can rely on it. So I can use sine squared theta and cosine theta. Oh no, getting ahead of myself. And sine theta. All right, based on that, what is this derivative? What was the derivative of g of sine squared theta? So 2 sine theta cosine theta, right? Then what's the derivative of h? Cosine theta plus sine squared theta times the derivative of, oh, I messed up bad. Don't let me do it. All right. Plus sine squared theta cosine theta, right? How does this simplify? Should be 3 sine squared theta cosine theta. Any questions there? What if I wanted to take the derivative of sine to the 10th of theta? Could we do that? Eventually. Now I can just keep building this up, right? So we could do that. What we're going to go over now is a way to kind of get to the end of that scheme without having to do all the intermediate steps. Any questions here? All right, so that's all for 2-4. So section 2.5 is all about something called the chain rule. All right, this thing right here. Can I find the derivative of this function right here?
Yeah.
How would I do that?
Separate them both, t squared minus 7.
Separate them both? What do you mean by that?
Like sine f of x and f of x and g of x. Like,
Okay, so you could use the product rule there, right?
yeah.
So let's do that. Let's say f of t is equal to g of t, h of t. What are g and h then?
T squared minus 7.
Yeah, both.
They're both t squared minus 7. All right, from there then, what's this derivative going to be? 2t times
T squared minus 7.
2 squared minus 7 plus, better be the same thing. So simplify, that comes down to 4t times t squared minus 7. So that's the first time I've seen someone suggest it that way. Totally works, obviously. Typically what people suggest is to FOIL that out and then take the derivative, which is going to get you in the exact same place. But yes, but this is something we can do right now, right? I know what the derivative of t squared minus 7 is. So if I'm squaring it, I have to accomplish that squaring before I can go further. Any questions about how we wound up what we did? What if I did this instead? Is this something we could do? Yeah, eventually, right? But we're going to set this up a new way. So product rule and quotient rule, we're breaking up functions into product of two functions and quotients of two functions. What the chain rule allows us to do is this. I'm going to set up functions as not multiplying, adding, subtracting, all those kind of arithmetic things that we've learned how to do. Chain rule works on another functional operation, and that's composition. So if I have some function g nested inside some function f, then I can take the derivative like this. So if we think about this kind of, let me draw like a block diagram here. By definition, if I say I have a function f of g of x or f circle g of x, if I were to evaluate this function, let's say I have some x value. What's the first thing you do with x to evaluate a function that looks like that? Right, but so how do I get that value? Like I'm going to feed x to one of those functions. Does it matter which one I choose first? Absolutely. So which one's it got to be?
F goes into G. F of X. Right. It is right there. Yeah. F goes into G.
F does not go into G. Yeah, it's just so basically, and let's just go back to basics. Let's not even talk about G yet. Let's just talk about X is some generic input. X is going to go in through G, and what comes out is going to be this new thing called G of X. But what am I going to do with G of X? That's going to get fed into this function F, and what comes out of there? F of G of X, right? So basically, when you do this composition of functions, you're taking some input of a function and you're running it through two different processes in series, in cascade, one after the other. So the reason I put that up there is basically when you take a derivative, you're going to take a derivative from either the end back or the outside in, kind of however you want to see it. So the first thing I'm going to do is take the derivative of what's the last function my input went through. Or what's the last function I had to use? F, right? So I'm going to take a derivative of f, but I want to take the derivative of f with respect to whatever its input was. What was the input to f? G of x. So that's one layer. Now I want to keep working back. What's the next function this input went through? Sorry. If I'm working back, so the very last function it went through was f. What was the second to last function it went through? G, right? So then I'm going to take the derivative of g. What was the input to function g in this case? X, so it's just going to be g prime of x. And those two things are multiplied by each other. So this thing right here is called the chain rule. This allows me to think of functions as composites of smaller functions and deal with their derivatives that way. Any questions there? All right, so now let's handle this nasty thing that I think you all agreed we could do if we had plenty of time. So now what I want to do is this. I would love to set this function up as a function composed inside another. So if that's my goal, can I decide on what g of t and h of t are? Maybe I should set up that block diagram again. T is going to go to what function first? Going to go through h first. Then it's going to get transformed into h of t. Then it's going to go through g. It's going to get transformed into g of h of t. So now let's try to think this schematically about this function. Let's look at f. What's the first thing that happens or what's my input there? Okay. Well, what's the input? Like the very basic of t, right? So I mean that all comes from, what does this function eat? T, just basic t. Right, so t. Okay, so we start with t. What's the first thing that happens to t? Well, so I'm asking these questions to kind of figure out what h and g are. But what I was getting at was, so if you look at this function, if you had a value of t, what's the first thing you would do with it? Square it. And then what would you do? -7. Garrett? So I think the inner function then is, I could really say the innermost function is t squared and then have a third function, but for right now, let's try to hold it to 2. So I think that innermost function is, let's just capture those two operations. First, I square an input and then I subtract 7 from it. Go. So t kind of follow along its path. It gets squared. It gets decreased by 7. After that happens, what happens to it? To the power of that 6-digit number 8. So then how can I represent that operation?
Would you say f of t to that power?
H
of t to that power?
It's eventually going to look that way, but right now I'm just going to do this. T to the 8, 6, 1, 5, 4, 7. Now I'm going to pause there because I think it's important to know why I just called it t. The reason I just call that T is, let's refer to this, as T goes through H, it's gonna get turned into what? T squared minus 7. And then I'm gonna take that T squared minus 7 and do what with it?
The power of that.
It just raises it to that power, right? So if I compose these functions in this way, I don't need to square it and subtract 7 again. It's just that already would have been handled if if I'm letting H do what it's there for. So I really think it's important to understand why G and H are defined the way they are. Please ask me questions. Let's stop here and talk about it as long as we need to. This is kind of the whole thing. Any questions? Solomon?
Why is h of t still t squared? If there's like if you're gonna multiply them together and there's a t on the top.
What am I multiplying together? Yeah, so there's no multiplication happening here. At least not in the way that I think you're getting at. So again, the 3 steps, basically the 3 steps that T is gonna take is, it's gonna get squared, it's gonna get reduced by 7, and then that thing is gonna get raised to the power of 861,547. Anything else about this definition? So now what we can do here is we can differentiate this from the outside in. So if I were to take the derivative of this entire function, I'm going to take the derivative of the outermost function, which we call g. But the way these functions are composed together, what is the input to function g? Is it t or is it something more complicated? Garrett? It's h of t. So I'm going to take a derivative of g, but with respect to h of t. So that's one layer, that's one link in the chain.
Multiply that by G by H prime.
Yes, multiply that by h prime of, what's the input to h?
T.
Just t. So that's the first layer. So now let's talk about what these derivatives of these functions are. Do we know what g prime of t is?
Would be 861,547 T to the power of that minus 1.
Yeah. So this is the derivative of 861,546. So that's that derivative. What's h prime of t? 2t. So then from here I can kind of finish this. So g prime is as we've written it there, right? If that's what g prime is, then what is g prime of h of t? So it's going to have the same basic structure, 861,547. Is it going to be t to that power?
It's going to be T squared minus 7.
It's going to be h of t raised to that power, which is, we decided a while ago that was t squared minus 7. So 851,000, no. 861,546. So that's that outer layer of the derivative, and I multiply that by what? 2t. And I would multiply those two terms, but I don't want to feel like doubling that number. That's fine with those. So any questions there?
So would that be as far as we have to go to get on the test?
I mean, unless I have to simplify it, but for right now, I'm focused on what the derivative is, and that's it. I mean, think that's a product rule, a quotient rule. Sometimes you can take a derivative and you're just left with a mess. I inherently trust your abilities to simplify things more in terms of the derivatives right now. Any questions here? All right, let's look at some more. Find the derivative of h of x equals tangent of 3x. So, can I think of this thing as the composition of two different functions. Okay,
Is that, and X is one.
okay, so I have these two things. Garrett's offering tangent of X to be one of them. And then 3X to be the other one. Using those two functions, can I set up H of X as the composition of F and G in some way? Is it F of G? Is it G of F? Is it neither of those? Solomon?
Would F of X be 10 or 10X?
So tangent by itself is not meaningful. You need to take a tangent of something.
Okay.
Go ahead.
So it'd be F of G of X.
F of G of X. Are we okay with that? Garrett? Isn't what, sorry?
Isn't that F prime of? Oh, yeah.
So I believe that F of G of X will get me tangent to 3X. What's the first thing that happens to my input here? My input X. It gets tripled. After it gets tripled, it becomes a new thing called 3X. What happens to it then? So then I agree with G being the first function, the inner function, and F being the second function, the outside function. Based on that, can I talk about the derivative of H prime? Or is there something you'd like to do first? Good. Let's do that. So let's find the derivative of F and the derivative of G. What is the derivative of F?
Secant square X?
Secant squared of X. And G prime? 3. I think that's enough to make the derivative happen. So what is the derivative of H?
Would be secant squared parentheses 3.
Secant squared of just 3? It would be 3X. And here's why.
Because G, not G prime.
Right. So when you take a derivative of, so first thing you got to do is take the derivative of whatever that last function is, the outside function, which I think we agreed was tangent X. So that's secant squared of X, right? But the way we've defined these functions, the input to tangent, the tangent of X function is not X. It is this slightly more complicated thing, 3 of X. So yeah, that kind of outer layer of the derivative is going to be secant 3X. Garrett? Yeah, and then multiply by 3 because that's the derivative of the next layer. And just because it looks better, I think. How we doing? Okay. All right. How about this thing? How would you like to break this one down?
You heard of this pair of root by putting the two terms to the power of 2?
So the 1/2?
Right.
I could do that. That's fine. So this equals theta plus 1 to the 1/2 times sine of theta to the 1/2. That'd be your F and G, right? So if we try to set it up that way, how are F and G related? Okay, so if we try to set this up as R of theta equals F of theta, G of theta, where F of theta is equal to theta plus 1 to the 1/2. And g of theta is equal to sine of theta to the 1/2. Can we take derivatives of f and g individually? You absolutely can. How? Like what do we need? I actually don't need the product rule for f or g by themselves. But there is something I need that might not be obvious yet. In fact, it most definitely isn't. Let's just focus on f of theta. F of theta equals theta plus 1 to the 1/2. Can I set that up as a product or a quotient or a sum or difference or composite? What's my input to f? What's the first thing that happens to theta? Okay, then I have theta plus 1, right? What do I do with that? Or what happens to it then? To the power of 1/2, right? You see how you have links in a chain there? So let me give you a contrast. What if I have a function k of x equals x squared sine of x? For k, what's my input? What's the first thing that happens to x? It gets squared. And then what? So I'm doing both of those things at the same time, right? Those are not happening in series, in a composite.
Because there's no parentheses.
Because basically, I mean, there doesn't always have to be parentheses, but what's important is the relationship of you like linking those steps together, linking the functions together. So if I say x equals 3, then I'm going to say, all right, I need 3 squared and also sine of 3. I'm not following a composite function structure there. But for f, the way you answered me, it sounds like we are. Because first I have theta, then I add 1 to it, and then I take theta plus 1 and I square root it. So because of that, I think I'm going to do this. Actually, let's just keep it the way it is. Knowing that f of theta is kind of arranged that way, I'm going to say this. Let's break it down one level further. I'm going to say f of theta is equal to a of theta times a of b of theta. And if I set it up that way, what is a of theta? And what is b of theta?
Theta is theta plus 1, a is 2 over 1/2.
Okay. Can I find a prime of theta? Can I find b prime of theta? Garrett?
A prime is 1.
A prime is 1.
Theta is 1 over theta.
Sorry, one more time. I didn't quite hear you.
It's 1 over theta or 2 times 1.
Should be 1 over 2
Oh, okay.
theta to the 1/2. All right, so can I do something similar with g? Can I handle that function g with the chain rule? So let's say g of theta is equal to c of d of theta. What's that outside function again? So what is c of theta?
The power of 1/2 or is it sine theta?
So the first thing that's going to happen to sine is, did I reverse what f was?
Yes.
I did, okay. Well, here we're going to fix that. So from here, C prime should be exactly what A prime, or yeah, what A prime was. 1/2 theta to the 1/2. What is D prime? Cosine theta. So from here, can I march ahead and do the derivative? Actually, we got 320, don't we? I'm gonna hold off and we'll finish this up next time. But we do have all the pieces. So I'll go ahead and stop here and we'll pick this up on Wednesday.